Alright, in this section, we're going to talk about this thing called binomial distribution or binomial random variable. This corresponds to the book section 4.3. This is very useful random variable. We're going to use this to analyze qualitative data set. Qualitative data set is mainly for us a lot of yes, no questions, right? So for example, let's say I'm working at the hospital, I surveyed 10 patients to see if they have coronavirus or not. Again, I test each patient, and each patient's either yes, they have virus, or no, they don't have a virus, right? So this is like a yes, no type of data set. So this is like one of the examples of qualitative data set. All right, so some terminologies here. 3 requirements for binomial distribution. We have a fixed number of trials. So from our 10 patients example, I'm testing 10 patients. So there are fixed number of trials. I'm going to try this test 10 times, right? So we use the letter n to denote this. So in that example I used, n was equal to 10. The outcome of each trial are independent from each other. Again, the concept of independent is one event. The probability of one event is not affected by the other event, right? So probability of one event is not affected by other events. Means if they tested me and you for coronavirus, the probability of me getting coronavirus, being positive for coronavirus, the probability is not affected by you having coronavirus. So that's what it means, that these are independent events. Number 3, each trial has only 2 possible outcomes, success and failures. So when you get tested, you either get positive, negative. That's all you get. So 2. That's why it's called binomial, because bi means 2, and the probability of success is constant or equal for each trial. We use the letter P to denote the probability of success. Another example we can think of is, let's say I flip a coin 10 times. So again, we decide, okay, we're going to try this 10 times, our experiment 10 times, right? So n is going to be 10. If I flip and then try to see how many times I get tails, whatnot. So first toss versus second toss. The probability of getting a tail on the second toss is not affected by whether or not I tossed a tail in the first trial or not, right? So each toss is independent of other tosses. And that's the second condition. And then third condition, each toss I had either tails or heads, so we only have 2 possible outcomes. And then probability of getting tail on each trial is always 50%. So that's our letter P. So here we have n is the number of trials. P is the probability of success for each trial. And you'll notice the letter Q. You don't use it that often, but you'll see a few times it's just 1 minus P. So this is a probability of failure. So what that means is if there's 20% chance that I test positive, that means there's an 80% chance that I test negative. So they always add up to 100%. That's why it's 1 minus P. Or you can think of it as 100% minus P. You notice that there's an X and there's a squiggly line and then B. It just is a shorthand notation for binomial. So here's the important part is the B part. So it means X is a random variable that is B, which is binomial. That is binomial for B. and n is the number of trials, and p is the probability of success. And the next notation, p x is equal to a, means what's the probability of getting a particular outcome? Of getting a particular outcome k many successes, right? So for example, if I tested 10 patients, what's the probability of getting 3 patients testing positive, or 7 patients, or whatever, right? And if I toss a coin 10 times, what's the probability I'm going to get 4 tails or 6 tails? 10 tails, is it likely that I get 10 tails? So we're going to investigate those kind of questions. And I'm going to do number 4. I'm going to have you try the next question. Suppose you flip a coin 10 times and counted the number of heads, okay? So the random variable represents the binomial. Number of, is a binomial random variable, is represents the number of h's, right? Out of 10 coin toss. The number of trial is 10, because you're tossing a coin 10 times. These are independent events because probability of getting outcome H is not affected by other outcomes, right? So probability of getting H on my second toss is not affected by whether or not I toss H on my first toss. So that's the definition of independent events. P here is the probability of success on each trial. So each time I flip a coin, there's 50% chance, so it's 0.50. Again, you can say it's 50%, or you can say it's 1/2, or you can say it's 0.5. They're all the same thing. Same here, Q is probability of failure. So in this case, I'm counting number of heads, so getting a tail is a failure. So probability of failure is also 50%, because this one is just 1 minus 0.5. Symbolically, we can describe B, and then I can say N is the first number, so that's 10. And then P is the second number, so either 0.5. Here I'm going to put 1/2. Okay, so I'm going to have you pause now and work on the next question, number 5. All right, we're back at number 6. So here we talk about how to actually calculate a particular outcome. For example, if I toss a coin 10 times, what's the probability that I'm going to get only 3 heads? Because that's possible, right? So here we try to actually calculate the probability. There's this kind of crazy looking formula here. We're not going to really talk about it. Fortunately, we have a calculator that's already programmed. This formula is programmed in already, so we'll just have to punch in the numbers, so I don't have to go through this process. So the calculator function key we're going to be using for this, and there's a separate video, also separate link. I linked it on the module as well, but it's going to be second. Then we're going to go to vars, which is the distribution function, and then we're going to scroll down to selection A, binom PDF. Is first time we're seeing it, and here I'm going to highlight P, and once you get there, basically you're going to input N, number of trials, and they're going to input P, probability of success for each trial. Then you're going to input K, the number of successes you're looking for. So basically it calculates the probability of getting exactly K many successes. Exactly K many successes. I'm going to underline exactly, because the next function key does something slightly different. So I just want to make sure we can tell the difference between that and that. So the next question says how to calculate probability of x less than or equal to k. Basically, this one calculates the probability of getting, notice it says x is less than or equal to k. The previous one was x is equal to k, right? That's why I underlined exactly k many successes. Here, I want to look at the probability of getting up to k successes, right? So I want to underline up to or at most. So not necessarily getting 3 exact successes, let's say for example, but up to 3 successes. That means 2 successes, that means 1 success is also they're all included. So this probably is going to be a little bit higher. And our calculator function key basically is very similar. We'll do second, we'll do vars, which is the distribution. And then we'll select B, binom CDF. And then again, we'll input N, P, and K. So it's almost same as before. Here, instead of picking binom PDF, here we're using binom CDF. C is for cumulative. So this is for, oops, where cumulative. Again, cumulative means you're including all the previous probabilities as well. So if I want to look at probability getting up to 3 successes, that means it includes 0, 1, 2, 3 successes as well. So these are 2 different function keys you're going to use for binomial, and there's a subtle difference. And one, the CDF will give you always bigger answers than PDF. So if I were to calculate what's the probability of that we get 3 heads out of 10 coin toss. Here I'll be using binom PDF function because I want exactly 3 heads. I'll put 10, that's my N, 1/2, that's my P, and then 3, that's my K. When I calculate this out, the calculator will give you 0.1171 blah blah blah. I can do 3 digits, so about 11.7%. Here I could have typed in 1 divided by 2. Here I could have just typed in 0.5. It would have given you the exact same answer. If the question was what's the probability that you get up to 3 H's, underline up to, out of 10 coin toss. In this case, I can do binom CDF because it's up to a certain number. 10, 1/2, and 3. So basically everything else is same. Here I use PDF. Here I'm using CDF. And I know my answer is going to come out a little bit bigger because this includes probability of getting 0 success and 1 success and 2 success and 3 success altogether. So if I do that, I will get the answer of 0.1718 blah blah blah. So that's 0.172. It's about 17, so it's slightly bigger. All right, I'm going to have you work on number 9 and we'll meet back at number 10. All right, for number 10, this is about sampling. So when we take a bunch of items, before we talked about how if we do not have replacement, then one person is selected and the person is gone, so the second person, the probability changes, so it's not independent. However, in our sampling, normally we take a sample and we don't sample the same person twice, right? So just for like practical reason, there are cases where we want things to be independent. So even though we take sampling without replacement, sometimes we're going to consider that as independent if the difference is not that big. So if we have our sample size, if sample size is small enough, less than 0.05, which is 5%, right, times population size. In that case, we're going to consider that sample to be independent sample. So for the next question, if we really randomly select 30 people from 5,000 without replacements, so without replacements, so normally it's technically it's not independent, but because sample size is pretty small compared to the population size, so sample size here is 30, and then 0.05 times 5,000 will be 250. Obviously 30 is less than 250, so we can consider it to be independent. So yes, because of this reason. Okay, I'm gonna have you finish the rest of the worksheet.